Okay, so now we're going to put together our knowledge of thermochemical equations, enthalpy, and revisit enthalpy level diagrams that we last saw in Year 10 Science. I'm going to put all this together and get a really good picture of what's happening to the energy in our reactions as they progress. So you'll remember that we've talked about the fact that in order for a chemical reaction to occur, it must collide with the correct orientation and energy equal to or greater than activation energy. This means that we must have enough energy to break the bonds of the reactants, okay, and then energy is given back when new bonds are formed. Okay, so when a collision occurs, it's only when the vibrational energy of that collision is sufficient to overcome the bonds holding the particles together that the reaction can be initiated. That energy requirement is referred to as the activation energy. So when we think about activation energy, this is essentially the hurdle that must be overcome in order for the reaction to occur. The bonds in the reactants need to be broken before it can proceed. This hump is known as the activation energy, the minimum energy required for the reaction to proceed. It is given the symbol EA or EA, so this is capital E subscript A for activation, E for energy. Okay, so it's going to be associated with the units of energy, kilojoules, and then of course it's chemistry, so mole. So in converting the reactants to the products, the reactant particles collide with sufficient energy, and we say that this is energy greater than or equal to the activation energy and the correct orientation. Okay, if these two criteria are not met, then the reaction will not proceed and the two reactants will just bounce off each other with no reaction occurring. We've seen these demonstrated before in terms of enthalpy level diagrams. So this energy profile diagram or enthalpy level diagram will be able to show us the enthalpy of reaction, the enthalpy of reactants and products, and the activation energy. If we have a look at this one here, we can see that the enthalpy of the reactants is lower than the enthalpy of the product. So we see energy being absorbed here to break the bonds in the reactants up to this maximum point here, which is our activation energy. So from the enthalpy of the reactants up to the highest point is our activation energy. Then energy is given back out as the reaction proceeds until it reaches the products. This difference between the products and the reactants is our enthalpy value. We can see here this would be a positive value, so the graph is showing an endothermic reaction. If we look at the next one, the enthalpy of the reactant starts higher than the products. The activation energy is from the energy of the reactants to the maximum energy requirement, and then the energy given back out is greater than that was absorbed. So excess energy will be given out into the environment. Delta H, the energy of the product is less than that of the reactants. Delta H will be a negative value. Okay, it's going to be a negative value. This is an exothermic reaction, and we can see that now in the labeling of these diagrams. When we show these, if we know what the reactants and the products are, we should include the formula for those on our enthalpy level diagrams. So the distance between the enthalpy of the reactant, H subscript R, and the top of the activation energy hump is the energy required for that reaction to proceed. So if we have a look at each of these, we can see that the exothermic reaction has the products at a lower energy level than the reactants. The endothermic reaction will always have the products at a higher level than the reactants because energy needs to come in from the system to make that reaction occur. Okay, the difference between the two is more energy absorbed, whereas the difference here, the difference in energy will be released. Let's have a look at what this might look like in terms of a VCAR question. This is a multiple choice question. We've been given an enthalpy level diagram, and we've been asked to know if the enthalpy change of the forward reaction in kilojoules per mole is which of these values. First of all, we can rule some out by looking at the fact that the enthalpy of the reactants is higher than that of the products. So we have this situation here. This will be an exothermic reaction. So we can rule out C and D straight away. Delta H is going to be the difference from the products to the reactants. So if I look, it's going to be this bit here. It starts, so delta H is equal to products minus reactants. So products is 50, 60, 70 minus 150 is going to be negative 80. So B will be the answer. Generally, you will be asked to sketch these. If lines or grids have been provided, then they are expecting a more accurate depiction where you can actually include the values. So if we have a look at this one, we're looking at the decomposition of ammonia, and it's been given as this equation here. We can see that the enthalpy value is positive. The activation energy is given as 335 kilojoules per mole. The activation energy for the reaction when the catalyst is added is 163 kilojoules per mole. So on the grid, we've been asked to draw a labeled energy profile diagram for the uncatalyzed and catalyzed reaction. So we've been given 0 as the starting point for NH3. We know that the energy as it progresses will have a delta H, so the difference between the reactants and the product is positive 92.4. So we would place our products at positive 92.4. So this is kilojoules per mole. This is 100, so 20, 40, 60, 80. So this is going to be around very close to 100. So I'm going to draw my products line in here, and that's going to be N2 plus 3H2, and I'm going to label that as 92.4 kilojoules per mole, so my examiner knows that's what I meant. Okay, and then we have the activation energy for the uncatalyzed reaction is 335. So I need to go from 0 up to 320, 40, so halfway through. I'm going to bring that across, and I'm going to make that my highest point. So now I'm going to draw the curve so that it reaches that highest point and then comes back down to my lower point there. That's going to be my enthalpy level diagram there. Okay, so this will be the uncatalyzed. I'm going to label this as being 335 kilojoules per mole. Okay, and then the uncatalyzed reaction. Okay, the uncatalyzed reaction is this one. Then we want the catalyzed reaction is going to be 163, so it's going to have a lower activation energy, 120, 40, 60, just over that. So now we can bring our catalyzed reaction, and it will have the same delta H value because delta H won't change. So this will therefore give me the catalyzed reaction will have a delta H of activation energy of 163 kilojoules per mole. Okay, so that there gives us the answer. Double check that we've included everything labeled. So we have labeled these. So EA is equals EA, and this is delta. We're going to have delta H is going to be this value here. And we have now met each of the criteria for this question. So when we're talking about activation energy, it is always a positive value. Breaking bonds is always an endothermic process, so it always requires energy to be put into the system in order for the bonds to break. All reactions will lose some energy on the formation of the products, but the difference between an endothermic and an exothermic is that the exothermic reaction gives more energy off to the environment than was absorbed to break the bonds in the reactants, whereas an endothermic reaction will only give a small fraction of that energy back, meaning that it had to absorb more from the environment than it gave back, so the temperature will decrease. So if there's a large activation energy, if you think about this, it means that the bond must be very strong. It takes a lot of energy to break those bonds. It has a high activation energy requirement. Large activation energy means that the collisions must need to be very energetic in order for the reaction to proceed. So if we have a look at something like this, the reaction between elemental nitrogen, nitrogen gas, and oxygen to form NO, which occurs in catalytic engines, okay, so combustion engines, has a high activation energy. So we don't see NO being produced in our atmosphere. This forms when lightning strikes, volcanoes inside combustion engines. It has a high activation energy in order for this reaction to proceed. Okay, so we either need to increase the temperature incredibly, okay, in order for this reaction to go, high pressure, various other things, but it's not going to happen at room temperature. Whereas if we look at something like the reaction of phosphorus with oxygen in white phosphorus, this will spontaneously combust. The activation energy is very low. So on a warm day, if you were to put a piece of phosphorus on the bench, it would start to melt under its own temperature as this reaction proceeds. Because the reaction is highly exothermic, the energy provided by the reaction occurring then starts to speed the reaction up. Okay, so reactions differ in terms of their activation energy, meaning that they will be easier or harder to get the reaction going. So other endothermic and exothermic reactions we should be familiar with, okay, include ionization. So you'll remember the definition of ionization energy is the energy required to remove an electron from an atom in the gaseous state. This means because there is energy required, it's going to be endothermic. Okay, there is an energy requirement in order for this to occur. We're going to go from a more stable to a less stable, more energetic state in the form of the ion. So therefore, it must be having energy placed in to remove that electron. Okay, changes of state, as we talked about earlier, can also be defined as endothermic or exothermic. Going from a low energy state to a high energy state is an endothermic process. From a high energy state to a low energy state is an exothermic process because the energy will be given off to the surroundings. That's it for our discussion on activation energy, endothermic and exothermic. Have a go at doing the questions on enthalpy level diagrams, and I'll see you in class.